This video is to give you an online practicum using a bow and arrow system, and we're actually studying the amount of work done versus the elastic potential energy that is stored in this bow. So here's the bow. It's actually been strung, so it's flexed. This is the relaxed position for this bow naturally. It's normally clamped down. There's a dowel rod here which represents the arrow. Here's a force probe which will show us the force applied at this point, so we pull it back further and further and further and further, doing more work on the bow and storing elastic potential energy in this bow system. And we can decide how far back it's being pulled for that force applied just by lining up a meter stick on the side. And I have that data for you, and I'll lead you through it as we go through in a spreadsheet. This is a closer view. You can see again this would be clamped down, and as we pull back further and further with this force sensor, then we can also see what the displacement is. Just a closer up view of the force sensor itself. So we can put a hook on it and pull. Force sensors can also be used to push along. But you can see it's pretty easy to tell how far back we've pulled the string. So here's a blank Excel spreadsheet which I've set up just for this practicum. And what we want to do is we actually need to find the elastic constant K for this target bow before we can go too much further. But we actually should collect the data beforehand. I've set this up with distance stretched being the unknown variable and saying that the applied force is going to be the known, because that's our given, our set point. But actually, the applied force depends on an independent variable, depends on that distance stretched, or that displacement, if you will. But it's just easier to follow the force probe and say, okay, at 5 newtons of force, this is how far we stretched it. At 10 newtons of force, this is how far we stretched it. So again, as you've experienced maybe with a bow, or just pulling on anything that's elastic, or even compressing something, it gets harder to go, harder to pull as you go along. So this is absolutely no different. So when you do the practicum, if you pull at 5 newtons, we have a distance stretched of 0.011 meters. 10 newtons, 0.023 meters. For 15 newtons, it was pulled back 0.036 meters. And just again, continually filling in the distance stretched based on the amount of force that we apply. And you can see that I've designed this spreadsheet so that it already sets up a scatter plot with a line fit to it. Just continue to fill in the data. If you were doing this in a lab situation, it would take a little bit longer. So is it perfect data? No, it looks like we have a little bit to the side of our trend line on one side or another, but that's okay. The trend line is there to give us an idea of what the underlying, how should I say, the underlying or the overview of the force versus distance actually is. So in reality, sometimes we have measurement errors, which you've no doubt experienced before. Sometimes the material itself is not as ideal as it might be. And if you look at this value, it's set up as a straight line. You might recognize y equals mx plus b. But that slope, that 292, that is actually the elastic constant. How could I figure that out a different way? Well, I could take these forces, and if you remember, finding the elastic constant, you take a force applied and divide it by how far something has stretched or compressed. Well, in this case, I could take these values, and I could actually add them all together and average a new K constant. But I'm happy with that trend line value. So the elastic constant is pretty high, 292 newtons per meter. So then you would take a measurement for the mass of the arrow, because anytime that we're considering energy transformations to something that's moving, we want to talk about kinetic energies and maybe even solve for speeds. So in this case, I would just take that arrow, that shaft, and put it on a scale and find out what the mass is. Not, it would read in grams, but I would convert to kilograms. And this particular arrow is actually 0.021 kilograms, so it was 21 grams on the scale. Now I'm going to release this. I'm going to actually shoot this. So if you've seen anybody, maybe Robin Hood, shooting an arrow, then the release height is actually from their shoulder approximately. So if I were to measure myself, my release height is about 1.4 meters. Now we start to get into the real energy conservation principles. We want to look at how much elastic potential energy should have been stored in this bow. If you know anything about graphical analysis, you could actually find the area beneath this curve here, the area beneath this line, and that would tell you how much work was done on the bow. And it should basically be also the amount of elastic potential energy that's stored in that bow. But again, trying to gain some practice with this elastic potential energy equation. EPE is 1/2, I'll just say 0.5, times the elastic constant, times x squared. Trying to gain some familiarity with this, let's just plug in the values which we've already found. So the final distance, it was pulled 0.159 meters, so that would be our x. So 0.5 times K, 292, it's already in newtons per meter, times X, 0.159 meters. And a lot of times people forget, you have to square this. Pull up my handy dandy calculator. I know you're in here some. Oh, there you are down the bottom. 0.5 times 292. Times 0.159 squared. I could easily do this in Excel, but for your sake, I'm doing it in a calculator. So about 3.69. What are the units? A joule. Is this a lot of energy? No, we didn't really pull it back that far either. So if I were actually going to shoot this target bow, I would have pulled it back a lot further. Now again, thinking about total energy is boring. Total energy doesn't change. How much kinetic energy should the arrow have after this launch? So I'm talking immediately after it comes off of contact with the string of the bow. It should theoretically have 3.69 joules of kinetic energy. Again, total energy is boring. If we had 3.69 joules of elastic potential energy, right when it's released, it should have 3.69 joules of kinetic energy. We're dealing with the ideal world. In the real world, you know that there are things like friction, there's air resistance to deal with, those types of things. So we would expect some conversion to thermal energy. Now we say, okay, what should that velocity be? It's shooting off. How about we go back to that little trick and we say that the speed is, there we go. It's actually, if we solve for the speed using kinetic energy, we say that kinetic energy is 1/2, I'll say 0.5, times the mass, times the speed squared. If you rearrange that algebraically, which I'll just do for you without showing you the steps, then you actually find out that the speed is the square root of 2 times the kinetic energy over the mass. Well, let's see, that's 2 times, what was the kinetic energy again? Oh yeah, 3.69 in joules. And we divide that by the mass. Oh, that was way up here. 0.021 kilograms. Again, handy dandy calculator. 2 times 3.69. I'm actually square rooting this whole thing. Make that clear. So divide by the mass, 0.021. Big number, right? It's okay. We can square root it. There we are. So 18.75 approximately meters per second. 18.75 meters per second. So just without doing any conversion, that's less than 50 miles per hour, but that's very fast. And it's just a very short extension. So imagine how fast it would be if we had pulled it back the whole way. Again, barring air resistance and those types of things, but still, it's a pretty powerful little system here. That's why they were involved in competition, surely, but the military for a long time, no doubt. So I ask you another question. How far should this go? Is there a predicted range for this projectile? And we're not actually going to shoot it, but I found that it's about 40 feet for this situation. We're not going to shoot the arrow, like I said. The actual range would probably be less than that because of air resistance. And again, this whole idea that we have to account for all forms of energy, and thermal energy is always a factor in the real world here. So if you have any questions, feel free to ask me. Don't forget, this is a video. You can go back, you can pause, you can open up Excel yourself and do this yourself as well. It's all about gaining practice in these, and I'm really just coming up with some real-world scenarios to help you apply these physics concepts. Don't forget, total energy is boring.